this perspective is half purposely set up. I accidentally set it up and decided I thought it was cool, because we're going to be talking about some facts about the brain, the mind, sleep, dreams today, or tonight, as it's more likely the case. Either way, I hope you guys bear with this new perspective. I thought it was kind of an interesting peek, sort of apt, given that me and you are two minds trying to understand ourselves. And although this probably isn't the way he meant the phrase, it's like Philip K. Dick's looking through a glass. Darkly. Very darkly. So either way, maybe this will allow us to more easily step back and take a third-party perspective about the events in our own minds that we so often just are so used to, that we take for granted. So let's have fun with this. Let's learn a little bit about the brain, about the mind that is certainly a part, if not all, created by the brain, and just give you guys something to relax to while we figure out a little bit more about the world than we knew, hopefully before you put the video on. With any luck, I'm not making you dumber. So let's open this book from 1987, mind you, to page 199. And here we are. This is going to be kind of weird. I guess I can't directly... What am I doing? Yeah, I guess I can't really directly show you the page. And even if I did, it would be a mirror image. Speaking of which, I guess finally my microphone will be on the right side. That should be your right, and this is your left, with any luck, right? Either way, that was a nice segue into our first phenomena about the brain. So, I don't know about you, I'm right-handed. I have a few people a few friends of mine who are left-handed. Apparently, many more people are right-handed than I realized. I thought it would be more like 70-30, right to left, dominant. But apparently the great majority, apparently it's closer to 95% of the population are right-handed. And it's been known for a while now that the left hemisphere of the brain controls the right hand and vice versa. So it's interesting that let's see. And I think the left hemisphere is also, on average, responsible for things in your life pertaining to orderliness and known or predictable things that you've already mapped out in your world, whether it's in you or external to you, or characteristics of behaviors of other people. And then the right hemisphere linked to your left arm, left hand, left half of the body generally. The right hemisphere is generally, we all are fairly familiar with, associated with creativity, but it is also more generally associated with unexplored, unpredictable phenomena. So when we're exploring things that we haven't, when we're exploring novel phenomena that we haven't yet come in contact with, we generally excite and use the right hemisphere of our brains. It's very interesting. So that's, I guess, explains why statistically the most creative of our population, though not all of them, are left-handed. So the speech and language centers of the brain are in the right creative hemisphere, which makes sense when you think about having to string together a series of words. It's generally, although the words themselves are probably stored in your longer-term memory, ordered in a certain way, in order for them to be uniquely strung together to create an original saying, sentence, communication. So there's a fair degree of creativity that goes into stringing a series of words together to make a unique thought. So, interestingly, the majority of left-handers also use the left hemisphere of the brain to communicate and control speech, but the percentage appears to drop to about 70%. But about 15% of left-handers appear to actually use both sides of the brain to control their speech. You know, I'm actually going to show you some maps of the brain that show where different areas happen to light up when being mapped out, I think, through an MRI machine. No, I just say scans. I don't know how recent magnetic resonance imaging would be. This book was written in 1987. But anyways, these areas of the brain happen to light up, undergoing these corresponding activities. So let's show you real quick. See if I can do this gracefully. Almost. So, here we could see in the top left, and there's resting with eyes closed. It's pretty much the whole brain is lit up. So that's interesting. It doesn't say sleeping. It just says resting. So that must mean that your brain is, no doubt your imagination is triggered quite a bit under that state. Looking at a moving object, we see the top and the frontal lobe, I guess. No doubt activating the vision, the visual centers. This is interesting. Reading silently. Hold on a minute. So here we have reading silently right next to reading aloud. So we have reading silently, there's much more sparse activity. And I wouldn't necessarily say less, but so reading aloud, it would appear that the active centers are much more interconnected. So I'm guessing that's the language centers connected up with the actual speech centers versus, so yeah, reading aloud, and I guess on top of the language and the speech centers, it would be activating the motor cortex, the motor areas associating with talking and speech, physically moving your mouth. And then down here we see listening to music at the bottom, and then listening to words at the bottom right. And these two definitely do not look drastically distinct, but they're certainly different. So I guess it would probably matter if there were words in the music, but they certainly look, I would say it's like more similar areas of the brain than they are different. So that's interesting. So maybe that tells us that music communicates in a way more similar to our brain than we realize, more similar to language in our brain. At least that's how we, because after all, I guess we are pretty intimately linked to our brain. More similar to language than we realize. And I was just thinking maybe I meant to light these candles I have right here. Speaking of lighting up certain parts of the brain, maybe we could use that as a nice segue into lighting certain parts of this candle. You guys see that? Okay. And there we go. Where should I set that? Maybe right there. It really is kind of cool in this perspective. You guys really get an idea of, well, I guess it's just another layer of complexity in the image that you guys are seeing. Now, the weight of the human brain, it triples between birth and adulthood. I didn't realize that. Reaching a final weight of about 3 pounds. So 3 pounds on average for men, 2.9 on average for women. By the time a person's 50, the brain actually, though, shrinks very slightly, losing about an ounce in weight, so that's 1/16 of a pound. Now, there's no correlation between brain size and intelligence. A man's brain is usually slightly larger than a woman's, but in both sexes, because the women's body are generally smaller than the men's, the brain size to body weight is proportional. There's actually 2 writers that hold the opposite for largest and smallest brain records. This was, for the largest, it was the Russian writer. I actually haven't heard of this guy before. So, that definitely, at least for me, means that there's no correlation between intelligence and size. So this is Russian author Ivan Turgenev in the 1800s, and his brain weighed 4.5 pounds. Then the brain of a French writer who I have heard of, interestingly enough, Anatole France, from the late 1800s, early 1900s, weighed only 2.25 pounds. So, the brain is divided into two left, and right hemispheres, each mirror images of the other. In most people, the right hemisphere correlates with control of the muscle and receives information from the left half of the body. And the left hemisphere monitors and controls the right half of the body, like we talked about. And then going back to the right, left-handed people distinction. In right-handed people, the majority, the left side of the brain, is usually concerned with such skills as reading and writing and talking. And the right hemisphere deals with artistic activity and the workings of imagination. The same is true for left-handed people, but left-handers are somewhat more likely to have their functions actually reversed in terms of how they relate to the hemispheres. Now this one's always something I'm really fascinated about. I've mentioned it before, and it deals with the number of connections within our brains. Our brains have 100 billion neurons. And this is after, of course this estimate isn't exactly accurate, but this is after, I think we're born with something like 400 or 500 billion neurons. And after there's a famous phrase in neuropsychology that goes, neurons that fire together, wire together. So after the first couple years of childhood development and the combining and emergence of neural pathways that are defined or help define actual regular activity of children, as they learn skills and develop conceptual categories for reality. All those extra neurons, they're kind of like an unchiseled statue. There's a lot of surplus material, but because it's not directed and oriented in any certain fashion, then they're really useless. They're not useful until they've been able to be wired together into certain structures in the brain that are impulses to action can be defined by as these neural pathways fire, as they light up, as they activate, I guess we might say. And as they activate, then you have definite, or at least more definite than the diffuse, unmolded mass of neurons that we were born with. So as we develop more and more and fortify modes of behavior and activities, then all these other neurons, they get chiseled away, and ultimately we have something like a structure that we might even call a personality that is developed out of this. And it takes 100 billion neurons, which are microscopic nerve cells. Each cell has a slender projection called an axon. And this axon links it through a fine connection called a synapse to other parts of the central nervous system. And some axons stretch the length of the entire spinal cord, which is about 3 feet. So you have some 3-foot cells. These are single cells, mind you, that are 3 feet long in your body, making them, of course, the longest ones that we know about. Each neuron is also linked to neighboring neurons by up to 50,000 connections, and these are called dendrites. So we have a neuron, and they have an axon, and at the tip of those axons we have dendrites. And think about, so we have 100 billion neurons. Let's see. 100 billion neurons times 50,000. So 100 billion would be, thousands, millions. So you have 6 zeros. We can do that with math. So we have 6 zeros for 100 billion. 2, 3, 4, 5. No, sorry, 9. So 100 billion is a huge number. And that looks like this. 100 billion. And then, let's see, we have times 50,000 neurons for every single one of those 100 billion neurons. Dendrites for every one of those neurons. So all that means is that we can effectively just add a 5 at the end of that 100 billion and add a couple more zeros, and we're going to get trillion. We would get quadrillion, trillion, billion, million, thousands, and ones. So, total, that is the number of connections that your brain is constantly made up of. That your brain is a part of, is a manifestation of, or your mind, I should say. So, yeah, when you think about now in awe of, complexities of chemistry or physics in stars and black holes and, really anything. There's the math that goes into modern chemistry and physics, not to mention biology, is astounding. And just imagine how much more complex you and I are than something like a magnetic field, or the electric current induced by a moving magnet or something. Well, we're certainly more, and that's a very crude example of what goes on in our phones and what goes on in our heads. Make this look like a game of Jenga, or tic-tac-toe. So it's, I just love emphasizing that, because when I learned that, and I still haven't fully grasped exactly what that means, that we literally, very literally, and I know that word gets overused a lot these days, but in its real sense, we are literally the most complex things that we know about in the world. So just keep that in mind the next time you're feeling down about yourself, or uncertain about interacting with other people. You're interacting with the most complex things in the world that we know about, maybe in the universe right now. And before you let that suck you out and make you anxious, just remember that everybody else sees the exact same thing. You, to them, are one of the most complex things in the world too. And just because you're complex doesn't mean that you aren't able to understand yourself. Just think about what privileges comes with that, with being such a complex being so adaptive, dynamic, being so layered and complex. You're able to learn, you're able to explore, you're able to create, and that's a beautiful, if mysterious thing, Life itself is fascinating, and we are at the pinnacle of the complexity of this weird phenomenon we call life. So just remember that next time you're doubting your own competence and ability. You are ridiculously complex, and that means that although you can potentially be an obstacle to other people, you harbor within you more potential for novelty and creativity than any other thing in the universe. You are the source you are part of a species, being human beings, Homo sapiens sapiens, that is a wellspring and specifically adapted to look out into the world, gather information, adapt to it, and overcome it and turn it into a virtue, turn it into a tool to be able to not only navigate the world, but navigate ourselves and navigate each other. So I think it's just incredible. I think we don't give ourselves enough credit for our abilities, our ability to socialize with other beings just as complex as we are. So yeah, that's my little optimism rant for the day. Now, new information reaching the brain from the senses is stored, analyzed, and acted upon by means of electrochemical impulses passing from neuron to neuron through the dendritic connections that we talked about. But just how complex information is actually coded into these impulses, or how it is translated back again is imperfectly understood. But it is known that the brain remains active to some degree around the clock, and that each day it triggers hundreds of millions of impulses, more than all the world's telephone systems put together in 1987, of course. The thumb, though, okay, this is kind of jumping to a new fact, but the thumb is so important in the human scheme of things that it has a special section, its own section in the brain, separate from the area that controls the fingers. So, that'd be a good time to tap out. And there's actually a part of the brain called the motor homunculus, and someone's mapped it out. In the thumbs, it's an accurate depiction of the human body. It's a picture of the human body drawn where the sizes of the objects, the certain parts of the human body, are proportional to how much of that part of the brain is dedicated to that part of the body. So, in other words, the picture has two huge thumbs. The back and midsection are very small because we don't have a lot of densely concentrated nerve receptors, pain receptors. But on the tips of our fingers, on our tongue is huge in this diagram. Our entire head in general is very, very large in this picture. And our feet and our hands are also on average very large. But in particular, our thumbs, we are all thumbs. It's so funny. Maybe I'll edit that in to show you guys. But it's an interesting picture of the human body and how our different areas are represented in our brain. Alright, so in the last little fact I'll read. And finally, nerve impulses to and from the brain. The actual impulses travel as fast as racing cars. They go about I don't know if you guys just heard that, but that was a really, really loud gust of wind. I think it knocked something over outside. Speaking of things traveling, so nerve impulses to and from the brain. The fastest impulses recorded in experiments in 1966 traveled at nearly 180 miles per hour. That's fast. Nerve impulses do move slightly more slowly in elderly people. They add up to about 150 miles per hour. So unfortunately, we literally slow down our thinking as we get older. But that's still, what is that, 30 out of 180 is 1/6. It's still only 1/6, so that's less than, it's maybe 15% slower. But that certainly by any means doesn't make up, it doesn't define cognitive activity as a whole. But anyways, I'm going to leave it there. I thought that was pretty interesting. As most things I talk about on this channel. And with any luck, you guys had a little fun looking at the brain through this and from this unique perspective. Alright, guys. And that's all for tonight. I hope you all sleep well. And I'll see you next time. Bye.